Good morning and welcome to the Arval Mobility Observatory webinar entitled Battery from Production to Recycling. The automotive industry is undergoing a major transition with a shift towards electrification. According to the European Automobile Manufacturer Association, the number of BEV passenger car registrations rose by 63% in 2021, and this growth is forecast to continue. In the third quarter of 2022, BEV account for 11.9% of total BEVs passenger cars registration. This is due to environmental challenges, but also to European regulation, such as the decision of the European Union to ban sale of new internal combustion engine vehicles from 2035. As a result, the demand for batteries has skyrocketed in major automotive markets in Europe. According to McKinsey, the demand for lithium-ion batteries is expected to grow by 30% a year globally by 2030. At the moment, China dominates the entire downstream EV battery supply chain and registered the largest share of global production capacity in the world. But the European Union has a strategic focus on the development of domestic battery supply chain. The European Commission launched the European Battery Alliance in October 2017 to address this industrial challenge. For Europe, the establishment of a complete domestic battery value chain is imperative for a clean energy transition and competitive industry. The first important project of common European interest on batteries was launched in 2019. In this context, most OEMs and battery manufacturers have built or are planning to build gigafactory either independently or through joint venture, with around 30 gigafactories announced in Europe. During this webinar, we will cover the full life cycle of the batteries, what they are, how to optimize the in-life EV battery usage, their relocation thanks to gigafactories in Europe, and then battery recycling. I am Yael Ben-Nathan, head of Arval Mobility Observatory, and I am very pleased to present you our special guest who will share their views on these key topics. Today, we will have the pleasure to receive Mr. Serge Pellissier, researcher in Licit Eco7, a joint research unit which is placed under the supervision of University Gustave Eiffel and ENTPE. His field of research are characterization and modeling of battery aging in transport application. And we will have also the pleasure to receive Mr. Yann Vincent, Chief Executive Officer of ACC, Automotive Sales Company, who has a very large experience in the automotive industry. After joining Group PSA as Industrial Director in 2014, he was appointed Chief Executive Officer of ACC in 2020. Good morning, Mr. Pellissier. Good morning, Mr. Vincent.
Good morning.
Good morning.
And thank you for joining and for accepting our invitation. So now we are going to start first with the explanation about batteries. What are batteries? Mr. Pellissier, could you please explain to us what are batteries, how they are built, and what is their evolution?
Yes, I will try. So this first image is to illustrate the different type and different shape of the battery. You have some either cylindric or prismatic or push. And next slide. Yes. First point when you said battery is to understand that if not there is different things behind, because you think of the battery of a mobile phone, it's in fact one cell. If you look at a computer or a laptop, the battery is in fact an association of, let's say, less than 10 cells. But in case of an electric vehicle, the battery is in fact an association of a large amount of cells. It could be several hundreds or even several thousand of cells. Next slide. Lithium-ion battery is in fact a huge family. And each member of this family has its own name. For example, you could find some LCO, lithium cobalt oxide, which are the batteries you could find in the mobile phone. But in the electric vehicle, you mainly find three types of battery: the NCA, like nickel cobalt aluminum, or the NMC, like nickel manganese cobalt, or the LFP, like lithium iron phosphate. So this different name associated with different chemical composition means also that each type of this battery has its own performance, its own characteristics. The first characteristic is, for example, the nominal voltage. You could see that the voltage could be as low as 2.4 or as high as 3.8. Another important performance is also the density, energy density in watt-hour per kilo. And you could see that in case of the three main battery used in automotive application, some has lower energy density than others. The NCA is the battery with a higher density, and the LFP is with a lower. But associated to this difference in energy density, some other benefits or some other drawbacks must be taken into account. And it's really important to, when you choose a battery, to take into account your specific constraint concerning safety, concerning autonomy, concerning stability, safety, the same, and the long lifespan. So, as an example, if you consider the LFP, you have a low energy, but you have a very high stability, thermal. You have a very high thermal stability, so it means a good safety. On the contrary, if you look at the NMC, you have, we must say it's a good compromise, because you have a high energy density and a good thermal stability and a good lifespan. So it's explained, for example, that the NMC is presently used by more or less all the West world car maker, like Renault, Ford, BMW, Volkswagen. And LFP is used by all the China's car maker, and most of the buses use this type of cells. NCA is at present used by some car maker like Tesla, but LFP is more and more used in the car industry. So after this, next slide, please. Yes. It's important to know that these cells are produced mainly at present in China, and in the future, some increase in battery production are expected in Europe and US, but this point will be treated by other presentation. And next slide. This increase in battery production is associated to an increase in the need for lithium-ion battery. And here you could see that the need is mainly due to the transportation application. And if you have an increase in the lithium-ion battery, next slide, please, you could expect to have an increase in the need for lithium materials. And when you see this so high increase in the need for lithium materials, you could wonder if the lithium is not a critical material. And this is explained in the next slide, please. If you look at the different materials you could find in a battery, which are shown here, you could graphite, silicon, titanium, niobium, manganese, lithium, and so on. Some of them are the part of the critical materials. But the lithium is not the more critical, because in the list of the critical materials, you could see that the higher risk are expected for the niobium, the cobalt, and the graphite, but not especially for the lithium, which may be a critical material, but not so high in the scale. This slide is also interesting to see that battery is not the application which use the more critical materials. It could be seen that the computer or the drone or robotics, they use more critical material than battery. Okay, next slide, please. What could be the future of the lithium-ion battery? Here on this slide, you see at the beginning today, the technologies use the graphite for the negative electrode, and you could see what I have previously presented, the LFP, NMC, and NCA technology. Between you have the liquid organic electrolyte, and these are the present technology, and people expect that in the future, concerning the negative electrode, you will find more and more silicium. In the positive electrode, you will find some variation in the NMC composition with more nickel and less cobalt. And in the far future, people expect to use some lithium metal with some solid polymer and inorganic electrolyte. This lithium metal associated with a solid polymer as an electrolyte will ensure higher density of energy, higher safety, higher lifetime. But the problem at present is that this solid polymer electrolyte needs high working temperature, around 80 degrees. So lots of work, lots of research are presently made to try to decrease the working temperature of this type of materials. Next slide, please.
Before joining in the second part of this presentation, I would like to precise that if you have any questions, please use the webinar Q&A feature available on the right-hand side of your screen, and we will address all these questions at the end of the presentation. Thank you.
Okay, now in the second part, I will try to give you some information about how to optimize the use of the battery in an electric car. So next slide, please. The first point to know is that if you look at the cell level, and if you look at the charging protocol of a cell, you must know that this charge have a limited voltage. So you must limit the voltage at the level of the cell. In this case, it's a 4.2. And if you go over this limit, you could have some deterioration, even some fire of the battery. Next slide, please. Why is it important? If you remember what I have said, a battery is made of an association of different cells. If you look at a battery with well-equalized cells, it means all the cells are the same state of charge and the same capacity. It's no problem when you discharge the battery or you charge a battery. You could use the full energy in all the cell, and you have no problem with voltage abuse of any cells. This is the left side of the slide. But if you look at the right side, in the case of a non-equalized cell, you may have some trouble when you want to discharge the battery, because you can't fully discharge the battery, because in some cell you have some risk of over discharge. And in the same way, when you charge the battery, you won't be able to charge fully all the cells, because some cells may have some overcharging. So first, no. Yes. So in case of non-equalized battery, you can't use all the capacity, and you have some risk of voltage abuse and deterioration. So what it means you need equalization. We'll see later. You need voltage control of each cell in the pack. And this job is done by the BMS, Battery Management System. Next slide, please. Now, a few words about aging. There is two types of aging. The calendar aging, which occur when the battery is neither charging, neither charge or discharge, and the influence factor are the state of charge and the temperature. And you have also the cycling aging, which occur when the battery is charged or discharged. The influence factor are temperature and state of charge, the same, but also you have the variation in state of charge and the current profile. You must know that the aging effects are two types. One is the loss of capacity associated with the loss of autonomy, and also an increase of the impedance, which is associated to a loss of power from the battery. Next slide, please. So if we look at what is the aging process, if we look, for example, for the calendar aging result, in the graph here, you could see the capacity loss in calendar aging for different duration. On the left side, you have the influence of the temperature, and you could see from this graph that the higher the temperature, the higher the capacity loss are. So from 10 to 55 degrees, you see the loss increasing. If you look at the effect of the SOC, you see that on the right side, you see that at the low SOC, 0 degree, for example, you have low loss. And if you increase the SOC, you increase the loss. So if you take care of the calendar aging, the rule is easy. Minimize the temperature and minimize the state of charge. Okay, next slide, please. If we are concerned by the cycling aging, it's less easy, because if you look on the left side, you see that effect at low temperature. For example, you start at 0 degree and you have the higher capacity loss. And if you increase the temperature to 10, 15, 25, you decrease the capacity loss. But if you go further, if you go on the right side, if you go to 35, 45, 55, you, on the contrary, increase the capacity loss. So it means that if you want to take care of the cycling aging, it's not so easy. You have to optimize, and there is two different mechanisms. So what it means for a car user or a fleet manager. Next slide, please. let's think that, for example, you are a car manager, a fleet manager, and you have a certain number of vehicles who arrive at the end of the day in the parking, and you're asking, how could I charge them? We'll see that it's different in summer and in winter. If you are in summer, the rule could be, the advice could be, charge as late as possible. Why? Because if you charge your vehicles as soon as it arrives in the car park at the end of the evening, at the end of the working day, and you charge it fully, it will spend all the night at a full charge and maybe at the high temperature, 30 or even more, 35. And in this case, you will have the maximum effect of the calendar aging. So the best way is to charge as late as possible. It means to wait in the middle of the night at 1 o'clock or 2 o'clock in the morning to start the charging in order to have the full charge at the morning at 6 or 7 or 8 hours. This is in summer. Okay, but you won't do it in winter, because in winter, if you charge as late as possible, what it means that the vehicles will arrive at the evening with its battery. It keeps the battery uncharged all the night. The temperature of the battery will decrease. And when you will start the charging at 2 o'clock of the morning, the battery may have the temperature maybe at 10 or 5 or even -2 or -5. And in this case, when you will charge it, you will create a high aging, cycling aging. So in this case, in winter, the advice is charge as soon as possible when the battery is still hot. You charge it and it will stay all the night with a full charge, but at low temperature, which is no problem concerning the calendar aging. So what you see here is that it's a bit more complicated, because if you have only one vehicles, it's an easy rules. But if you have 10 or more vehicles, a complete fleet, well, it could be a great advantage if you have an automatic tool to adapt the charging protocol. Next slide, please. And this is my last one. Some other example of good practice may be the following. First, the partial charges are not a problem. So there is no need for full discharge. You could charge as soon as you want, and there is no need for full charge. And on the contrary, the full charge are not welcome, in fact, because it decreases the lifetime of the battery. So full charge must be used only if necessary. But all the car maker advise you to make some full charge from time to time. Why? Because if you remember, the BMS must make some equalization, and usually equalization is made at the end of the charge. So this is why it's compulsory to make from time to time some full charge. Few words about fast charge. First, you must know that the fast charges are not possible at high value of state of charge. At higher value than 70 or 80, the power is limited by the BMS, so no fast charge. And the fast charge also needs a special thermal management, because sometimes you may have to heat the battery before starting the fast charge in order to decrease internal resistance. But during the fast charge, you may have to cool down the battery. So the fast charge must be identified as problematic, because they need some special thermal management. I think it's time for me to give the parole, to give the Carol to the other.
Okay. Thank you, Mr. Pellissier, for all this explanation. We will have a few questions after the second part of the presentation. Now, we will have the pleasure to speak about gigafactories. Mr. Vincent, you are the Chief Executive Officer of ACC. This company aims to produce sustainable, affordable, high-capacity, longer-life batteries. And your motto is accelerating sustainable mobility for all. Your company is a joint venture between Saft, Stellantis, and Mercedes, created in 2020. The first gigafactory is due to start operations in 2023 in the Hauts-de-France. And the next to come will be your second gigafactory in Germany in 2025. And a third one was announced in Italy. Mr. Vincent, could you please describe your project for the ones who don't know you?
So indeed, the company was set up 2 years ago. And basically what we've done so far is we've created an R&D center close to Bordeaux, which is operating since 1.5 years. We've built from scratch a pilot plant with pieces of equipment which are scale 1. This pilot plant is operating since the beginning of this year. And currently we are in the process of building our first gigafactory in north of France. So we've started the construction of the building beginning of this year, and we will indeed deliver our first customer end of next year. But I think it could be worth showing you a video if you don't mind. So let's try to have this one.
Thank you. We don't see the video yet.
Okay. Sorry, I think it was difficult, so we won't show the video.
No, but in this case, no, in this case, if I may, you can use share.
No. We don't show the video. Okay. Sorry. It was interesting indeed to highlight the fact that we have concretely started to build. So it's not only, let's say, PowerPoint, but it's real stuff with a pilot plant, with an R&D center, and with a gigafactory which is under construction.
Okay. Could you please explain to us what are the key success factors of your project in Europe?
Well, let's say that our industry is a very capital-intensive industry with a process which is very sophisticated, a manufacturing process which is very sophisticated. To give you some insights on the intensity of capital which is needed, let's say that in average to build 1 gigawatt hour, you need between 70 and 80 million euro. And the demand in Europe in 2030 is forecasted to be around 1,000 megawatt hour, 1 terawatt hour. So it gives you some insight on the intensity of capital which is requested. And from that perspective, relying on the three strong shareholders, such as ours, is obviously paramount. SAF Total, Stellantis, and Mercedes. The second point is the sophistication of the process itself. So we are producing the electrodes, we are bringing the electrodes into a cell, and then we are bringing the cell into a module, and the car manufacturer is bringing a number of modules in what we name a battery pack. The production process of the electrodes, as well as the mechanical part of this process to eventually produce a cell, is particularly sophisticated. And for this one as well, relying on a company which has the experience of producing electrodes, such as SAF Total, is paramount. Relying on partners which have an experience of mass manufacturing is as well paramount. And one more time, that's the case for co-shareholders.
Okay, and in terms of mining, management of raw material, and so on, how do you manage this part?
Well, it has been previously mentioned that indeed we are relying on materials which might be scarce in the future, and basically there are three of them which are in our perspective critical: lithium, nickel, graphite. For these materials, we are relying on our own customers, which are striking deals with some mining projects. So that's the case for Stellantis, which has signed a deal with Vulcan, a German company which will extract lithium from Rhine through geothermal manufacturing or engineering. By the same token, Mercedes has signed a deal with Rocktech, a Canadian company. And in those two cases, it's a lithium project. In those two cases, there is a long-term offtake agreement signed by Mercedes, by Stellantis, with those projects, and securing a share of the lithium we will have to utilize. That's one. Second, we are relying on our supplier, on our chemical supplier. So the first chemical supplier we selected is Umicore, a Belgian company, and they are themselves striking long-term agreement deals with some mining projects. And eventually, the last one is we are dealing with directly, ACC, with some graphite projects. So we've recently announced the signing of an agreement with Talga, which is going to run a natural graphite project in Sweden. So that's the way we are securing those key components supply.
Okay, and what are the challenges you face in Europe? The other challenges are, I mean, regarding regulations, carbon footprint?
Well, I mean, they are very numerous, the challenges we're facing in Europe. Let's say that the first one is that we are creating an industry which didn't exist only 2 years ago. We should remind that 2 years ago, there was only one gigafactory in Europe. I mean, almost only one, let's say. One of LG, the Korean company, which started its operation in 2019. And apart from that, limited capacity in Hungary and in the UK. So the major challenge is to build this industry almost from scratch, and that's our case. That's the case as well of Northvolt. And to do so, we need to rely on some competencies which don't exist in Europe, and we are looking for those competencies in Asia. So we have recruited people coming from Korea, from Japan, China as well. That's the first one. The second one, which is, let's say, which would be more a challenge for, we do believe, our Asian competitors, is establishing in Europe what we name the carbon passport, the CO2 passport, because we acknowledge that on one side the EV car is not emitting CO2, but on the other hand, the process of producing batteries from the mine till our own process might be significantly CO2 emitting, and therefore it's important that we reduce as much as possible these CO2 footprint, and one of the way is to rely on a real green energy, and from that perspective, we have a lot of assets in Europe, and particularly in France, let's say, with the nuclear power, which is zero CO2 emitting, compared to let's say China, which is heavily relying on coal energy, and therefore it's important that this CO2 passport does reflect the reality of the production from the mine till our production. It will be very important for our customers, will be very important for the European citizens to guarantee that we are as less as possible CO2 emitting.
Okay, thank you very much. When the first batteries will be produced and available on the market?
Well, we got, so first of all, we started to produce batteries in our pilot plant, and those batteries are delivered to our customers for their own internal tests. But we will deliver to Stellantis end of next year the first batteries which will be assembled on serial cars to be launched in 2024. So end of next year, the first commercial batteries, let's say.
Okay, and what about solid state battery? Could you please tell us more regarding this technology and what will be the impact on the market?
Well, solid state battery is something any cell manufacturer is working on. The main advantage we can infer from this technology is that you don't have any more safety risk, which are existing with the liquid battery because of the electrolyte. And the fact that this risk does exist with the liquid battery drives the car manufacturers and the cell manufacturers to install a number of devices to avoid this risk. And those devices, they are consuming space, they are costly. With the solid battery, when you don't have any more this risk, you can get rid of all this stuff and hence replace the place which is hidden today by those devices by energy density stuff. Hence, you can increase significantly the energy density. The problem is that this technology is not yet mature. So all of us, we are working on. We've signed recently in September a partnership with a Taiwanese company named Prologium, which is highly promising, but I can't say for sure that we are ready for a given year. We are shooting for, obviously, but there's still a lot of hurdles to overcome.
Okay, interesting. Thank you. Regarding the current battery, during the life cycle of the battery, can we repair battery?
Repair, I won't say. Repair, I won't say.
Okay.
You can disassemble the battery pack from the car. You could change one model of the battery, it's not an obvious return. So I wouldn't say that it's the most likely.
Okay, interesting. And do you think that a second-hand battery market will exist?
Well, I think it's likely. We consider that roughly after 10 years of usage on a car, the battery doesn't have any more the specifications which are needed for the car usage. But it might be utilized for storage of energy. So that's a possibility. Let's say that it will be the choice of the storage of the energy storage companies. In 10 years time from now, they'll have the possibility of either getting a used battery, which will be most likely cheaper, or to have a brand new one, which will be more expensive, but whose technical capabilities will likely be better in 10 years time from now, because we will have improved. So it's feasible. They'll have to face, and in 10 years time from now, the car manufacturers will have to face either we recycle the battery or we utilize it still 5-6 years more in the storage of energy.
Okay, thank you very much. And now, if we can tackle the last topic of the presentation regarding recycling.
Yes.
So, yeah, what is the status of battery recycling in Europe?
Well, I mean, first of all, it's obviously very important for 3 very different reasons. The first one is regulation, which will make over time mandatory to use more and more recycled materials into the production of our own cells. So that's one. Second, for obvious ethical reasons, we don't imagine that we could get rid of our batteries at the end of their life into waste. And the third one, which goes back to the question of raw material sourcing, which is that at some point of time, when the flow of used batteries will get significant, to some extent, it will be the new mine. So for those 3 reasons, we are very much interested by recycling. It's a difficult activity. Already some companies are performing that. At the case of our chemical supplier, Umicore, which is already able to recycle batteries. On our own, what we are striving to is to make our batteries more than 95% recyclable. And it has to do with the choice of the materials, particularly with the choice of the materials. So we are selecting materials which at the end will be indeed recyclable.
Okay, perfect. Thank you. Thank you very much for this presentation. Now we are going to have a look on the questions coming from the audience. Serge, could you give us an overview about the current? We were speaking about recycling batteries. So could you please, Mr. Pellissier, give us an overview about the current recycling opportunities?
Okay. Yes, I can try to say a few words about this. The first point, at present, the only battery which are recycled is the battery from the laptop and computer and the phone. So it means it's LCO technology, and from this battery, the main materials who is recycled is cobalt. As it was said, there is no there is not a lot of EV batteries to be recycled, so it's not a real industrial process now. But the main problem is that, as it was said, in some battery for EV, there is no more cobalt. So this will be a real challenge to change the economical model, the chemical process, to adapt all the recycling industry to this maybe new type of cell. And the question is, do we have the capacity to make a different recycling process for the different type of battery? This is a real challenge for the future.
Okay, thank you. Mr. Vincent, do you want to add something regarding this question?
No, I think it's obviously very important, and one of the driver of the recycling is indeed the business model, and you will easily accept the fact that the more costly the materials in the battery, the more interesting is the recycling business, and the other way around. Just an example, if you have LFP batteries, so lithium iron phosphate, those are materials which are not very cheap, but much cheaper than the nickel and the cobalt. But being more cheaper, it makes the recycling activity business-wise less interesting. So that's a challenge. And the second challenge for the recycling companies will be to reduce their energy and intensity, because it's highly consuming energy. So meaning that all the process which will be developed in the future and which will save energy are more than welcome.
Okay, thank you. I have another question about recycling. The European Union has created a regulation that requires that all batteries have to be 100% recyclable. Is this then still an utopia?
Well, I'm not aware of this one. I mean, obviously, I'm very much aware of all the discussions taking place at European level on the question of batteries. What's clear that the European community is enforcing regulations, making mandatory to increase over time the quantity of recycled materials within the production of new cells. That's one. So over time and per material, by the way, with different numbers for cobalt, for nickel, etc. The second point is that it's clear. I mean, I'm speaking for the car manufacturers, but that's very clear for them that they have the duty of getting the batteries at the end of the usage and to recycle them and to do something with them. That's the duty of the car manufacturers.
Okay, clear. Thank you very much. Regarding the cost competitivity of the price of batteries compared to Asian market, do you have any idea regarding the competitivity of the European batteries compared to the Asian one?
I mean, we don't have to be afraid with this one. We don't have to be afraid with this one for let's say a set of reasons. One is that the labor cost is a limited share of the total cost of a cell. And the disadvantage we might have in high-cost countries, which is the case of most of European countries, versus low-cost countries, and we're thinking obviously to China, is pretty limited. On the other hand, we have a significant advantage on the energy cost, which is balancing the slight disadvantage on the labor cost. And finally, the last point is that logistic costs for a battery might be significant. So to transport a battery from China or Korea to Europe is not cheap, and we get rid of this cost. So I can tell you that even though our customers are as well our shareholders, they are highly demanding, and they are comparing our selling prices with the ones they get from the competition. And so far, we are in the race. So I'm pretty optimistic on this one.
That's a very good news. Thank you. I have a question for Mr. Pellissier. When you spoke about the risk linked to the materials contained in a battery, ranked on a risk scale, were you relating to scarcity risk, geostrategic risk, transportation, or storage issue? Please.
Well, I'm afraid I'm not the right man for answering this question. I'm not a specialist of this type of study. I just mentioned that if you look at the study made by people who are in charge of this question, and from this study from I think the European Commission, they said that they make this scale of different materials, but I'm not able to discriminate in this risk, the risk from the transport and so on. No, I'm sorry.
Okay, thank you. Do you want to add something, Mr. Vincent, on this question, or not really?
Well, I mean, the criticality of the raw materials has not to do with the existence of resources themselves. They do exist. The criticality comes from mining projects existing or not. So, and it takes time to implement a new mining project. That's one. It has to do with the localization of refining activities. And just to take an example, almost 100%, not 100%, but a big share of refining of natural graphite is performed in China. So that's a risk, regardless of the geopolitical dimension of the risk. The mere fact that it be concentrated in only one country is in itself a risk. So those are the risks we might mention concerning the raw material.
Okay, thank you. And how technology will impact the range of the BEV in 5 years' time?
Let's say that we are working on two very different items. One is to increase the energy density of our cells. And I mean, let's say that the autonomy of a car is directly linked to the number of cells and to their energy density. The more cells you have, the higher the energy density in a cell, the more autonomy you have. And you've seen most likely that one of our shareholders, Mercedes, they did announce on a car more than 700 kilometer autonomy. But let's say that for us, it is bringing as much energy density as possible in the cell. And the second point, which is very important, is the time to charge. And it goes to what Mr. Pellissier did explain previously on the fast charge. It's clear that the quicker the charge, the more likely you will accept a lower autonomy, and the other way around. if it takes a long time to charge, then you will request a very high autonomy. So we are working on those two key, let's say, drivers for the choice of the customer.
Okay, thank you. About battery management charging, did we reach the maximum technology, or do you see more improvement like with artificial intelligence?
Well,
I'll leave maybe Mr. Pellissier answering this question.
Yeah.
What I could say, and maybe you would complete better.
Thank you.
As I said, the charging of a large number of vehicles could be a challenge, because as you couldn't start all the charging at the same moment, because it will mean a very high value of the power. So you have to share the time, to share the energy, and you had to do this taking into account aging, the constraint, the operational constraint of the different vehicles. So in this case, you really need to be helped, and for sure, artificial intelligence may be a good help for the management of the charging battery. Yes, I think it in the future it may be a good point.
Okay, thanks.
Sorry. That more and more we are speaking of vehicle to grid, and it's fair to say that the car in itself is a storage device, and you might utilize these storage device to cope with fluctuations in the grid. But by the same token, it's clear that it has to be managed, and it's not an easy stuff to be managed, as has been explained by Mr. Pellissier, and hence the AI might be a tool for doing so.
Okay, thank you. We will take a last question. If there should one day be a second-hand market for batteries, I guess the price will be closely related to the remaining capacities of the used battery. Do we currently have the technical means to precisely assess this and therefore set price of second-hand battery in a transparent way?
Well, I'm not sure it'd be that easy, but it's clear that the demand for storage are very much different from the demand for automotive usage. And that's the reason why it's possible to utilize for storage devices.
We have an issue, I think.
30% of the initial capacity, then it has to be utilized for storage, and clearly it will have a lower cost than the brand new battery.
Thank you very much. Mr. Pellissier, do you want to add something?
Yes, concerning the second life battery, I think we must be clear on the fact that it's a real challenge, because to assess the capacity, the performance of a second life battery, it's quite a huge job. If you want to measure precisely which element which is is in default, it might be very long time process. So and it's not so easy you don't have to imagine that you could take the aged battery and just put it on the other application, because you either have to to adapt the management of the energy. Either you have to dismantle the battery to make a new one. So in any case, there is a lot of question, economic, industrial, and scientific question about this.
Okay, thank you very much. We are at the end of the presentation. Thanks a lot, Mr. Vincent. Thanks a lot, Mr. Pellissier, for all the information shared today. The webinar is recorded, so the replay will be available on our website in the coming days. Thanks a lot for all the questions we have received. Unfortunately, we will not be able to answer to all of them, and we hope to have the pleasure to receive you in our future webinar. Thanks a lot. Goodbye, Mr. Pellissier and Mr. Vincent. Thanks a lot for your participation.
Thank you. Goodbye.
Thank you.